All right, we survived day one of 6-1 law of sines. I'm looking at those ambiguous cases. There's a lot of different things to think about. We have one last example to finish up from that. We haven't done kind of the last situation, and then we're going to talk about area of triangles, how we can use things like law of sines to help us find the area of a triangle a little bit different way, and then to model a real life problem. So we're going to do some of that as well. So I want you to take a peek back at your ambiguous case kind of layout here. Remember, we always look at what we're given is the side-side angle. So we have two sides and an angle that's across from it. And that side-side angle, it really matters what the angle measurement is. So we broke it down into if that angle that we know is acute and if the angle we know is obtuse. So that's how we were doing our conversation. So if the angle is obtuse, it's really nice. Either it works or it doesn't. If the side across from the angle is shorter, there's no solution. If the side across from the angle is bigger, there's one solution, because remember, if it's obtuse, it's the biggest angle in the triangle. The side across of it has to be the longest. For the acute situation, we have more of a conversation to have. It depends on the size of the side across, how that compares to the other side you're given, but then also the height. So we have this calculation we talked about yesterday on that part one, how to calculate that height. So it's the sine of the angle you know times that other side. And again, the A, the B, the C, whatever the labels are, doesn't matter. It's just the angle you're given. So we have to always think of it that way. We're calling it angle A, but it doesn't have to be angle A. But remember the different cases that we talked about yesterday. We did the situation where the side that you're given across from the angle is shorter than the height. Can't draw that triangle. It's physically impossible. That would be a no solution. We talked about, hey, what if the A is actually equal to the height? Then it's the perpendicular distance on that right angle. So the only is going to be one triangle there, and it's going to be that right triangle. So if it's actually equal to the height, that's one. We also talked about the situation where the side across from the angle you're given is actually longer than the other side that you're given. What that means is there's only one way you can draw that. It has to be going away from that vertex A. So one triangle. So we dealt with all of those. What we haven't dealt with is this two triangle scenario where the A is bigger than the height, which means we can actually physically draw the triangle, but we can either draw it as an acute triangle with the A going away from vertex A, or we can swing that side A back and have it come back towards vertex A, and then we make an obtuse triangle. So we have this obtuse triangle here instead. So that's the case that we're going to look at today. We're going to talk about what do we do and how do we find that second set of solutions. So let's get back into your note-taking guide here. We're going to draw some pictures, try to write out as much as we can to make sure we understand what's happening. So here's what we're given. We're given one angle and two sides. So this is a side-side angle. I know it's side-side angle because the side is across from the angle that we're given. Same letter, so we know that that's what's happening. I'm going to try to go ahead and draw what this would look like so we have an idea of what's happening in this situation. I think it's nice to have a picture. So we have our angle A, which is 25 degrees. And we have our side A, which is 26, and then we have our side B, which is 54. So in this case, so let's kind of go through what we know, and we can talk about how we know what's going to happen. We're given an acute angle, so we have an acute angle, so that means we know we're going to have one of those four options on that sheet because this is side angle and the angle we're given is acute. So I know I'm living in this world right now. To be able to figure out what happens, I need to figure out my height and I need to see how that side compares with the other side. So the first thing I'm going to look at is that side A, 26, is definitely less than the 54. So the side A is definitely less than the side B. So when I think about what's happening, I can rule out some things. We definitely do not have where A is bigger than B. Can't really rule out anything else yet though, because I need to figure out the height. So we're going to solve for the height next. So we're going to figure out what the height would be in this triangle. So the height is B times the sine of A. So that's going to be 54 times the sine of 25 degrees. So let's go ahead and calculate that height. If you can type that in, 54 times the sine of 25 degrees. See what you get. And I'm coming up with about 22.8. So I want to see how that compares with everything else. So 22.8 is less than the 26. So the height is less than the A, which is less than the B. So what that means is, since A is bigger than the height, I can actually physically draw that triangle. So if I put the height in here, This is what's the 22.8. We just did that in this triangle over here to figure out our height. So 22.8 is shorter than the 26. So I can physically draw that. It works. But because it's also this A less than the 54, that means I could either draw it the way I have it drawn there. So this would be kind of like set number 1 here for my solutions. Or I could also draw it, and let's take a look at what the other option is. So I'm going to go ahead and draw this triangle again. So I have my 54, I have my 25 degrees, so this is my angle A. Instead of the 26 going away from that vertex A, I'm going to draw the 26 coming back towards the vertex A. So the 26 would be here. Now remember, we still have the height of our triangle, right? The height is over here in this case, which is the 22.8. We just swung this side, that 26, over, right, in this direction and had it come down here. So we want to make sure that we're thinking about what that is. So that means we get a new, this was our angle B that we'd be able to solve for. We get a new angle B. We're going to use this prime notation. That would be right there. Right, so if we swing that over, and I'm going to put it in this one, it would look like this. So this new B would be over here. So when we're thinking about our two cases, our two sets, we have the original blue one that goes all the way out to that angle B, and then we have this obtuse option as well. So we want to think about how we would calculate that, and we're going to go through and solve for both of these. So I know it's going to be two triangles, so our assumptions here. I know it's going to be two triangles, and my reasoning are these two pieces right here. I know that it is bigger than the height, less than the other side, and it was an acute angle that I was given in side-side angle. So the reasoning behind telling that it's two triangles is right there, and that's what they're going to look like. All right, so let's go through and find our set number 1. So we're going to actually calculate the solutions for our first set of answers. So we would do that exactly like we did yesterday. So we know everything about side A and angle A. So 26 is to the sine of angle A, which is 25 degrees. Now for side B, we know that that's 54, and that's as sine of angle B. The only thing we can solve for is that very first angle. So I'm going to be solving for, in this set number 1, this angle B. So we're going to go ahead and cross multiply and divide. So sine of angle B would be 54 times the sine of 25 degrees divided by 26. And remember, that's what the sine of angle B is. So ultimately, to calculate angle B, we're going to need to do inverse sine of 54 times the sine of 25 degrees divided by 26. Be really careful on your parentheses again, right, that we're putting parentheses where they belong. So go ahead and type that in, get your calculation. All right, so double check. I just typed it all at once, but notice I finished off that parenthesis after the 25. That's really important. So angle B, we're going to go ahead and round to 61.4 degrees. Notice that's in set 1, so that means this is 61.4 degrees. All right, well, we have two angles in our triangle then, so it's always pretty easy to find that third angle. So we're just going to subtract from 180. So we're going to find the third angle. So we're going to do angle C is 180 minus the other two angles we know. So the 0.4, and then our original angle measurement, which was the 25. So go ahead and do that calculation. Let's see what our angle C would be. So go ahead and pause and calculate that out. Looks like it comes out to be 93.6 degrees. So that would be our angle C and that original triangle. So I'm going to go back up and go ahead and fill that in. So angle C would be up top here. So that is the 93.6. Angle C up there. All right, so what's the only thing that we don't know? Well, we don't know the side across from it. So we have to find out that little c. So we're going to go ahead and use our law of sines. So we're going to find the third side. So to find our third side, we're just going to set up our law of sines. Go back, though, and use the given information. We don't want to use rounded answers. So we're going to go back and use everything about side A and angle A. So 26 is to the sine of 25 degrees, as little c is to the sine of 93.6. We really can't avoid using a rounded number there. That's the best we can do. All right, so we're going to go ahead, cross multiply and divide. So little c is going to be equal to 26 times the sine of 93.6 degrees divided by the sine of 25. Go ahead and pause and do that calculation again. Don't forget about your parentheses. Finish those out so you know you're dividing what you think you are. All right, and by coinky-dink here, it ends up to be the same as what the angle is. It does not obviously always happen, but our side C is 61.4, and that was in feet, I believe. So we have that third side, which is across from angle C. So this one would be 61, this side down here, 61.4 feet. All right, now that's our set number one. That's when we have that acute triangle. So the first set is when the triangle was acute. In other words, that first angle that we solve for um, ends up being acute. So set number one is when angle B is acute. Set number two is when angle B is obtuse, all right? And we want to figure out how would we solve to figure out what that new angle B value is going to be equal to. So I'm going to draw the triangle again so we can do the work and think about what that is. But I think if we look back at this original picture, we had our angle B. Remember, we swung this side A back towards vertex A, and we ended up with this red one. So what I want you to think about is look at this triangle right here. So this is also 26 then when I swing it back the other direction. If you look at this red triangle, that's an isosceles triangle. Both of these sides are 26. Okay, what do you know about isosceles triangles? Well, not only are the sides the same, the base angles are the same as well. That means this angle is 61.4. That means the angle on the other side would be 61.4. So we're trying to calculate the angle over here on the other side. Well, don't those two angles make up 180 degrees? So if I know that's 61.4, how would I find my new angle B? Well, it's going to be the supplement, or 180 minus our original angle B, because they would add up to 180. So the fact that it really ends up to be an isosceles when I swing that over, that's how we're going to calculate this new angle B. It's always going to be 180 degrees minus the original angle B that we came up with originally. So that new angle is what we need to calculate first. Always going to be the supplement. That's an easier way for you to say it. Supplement of that first angle that you solve for. So I'm going to call it B, but realize it's always just the first angle that you solve for, because it doesn't have to be B, right? That we could have any label on there that we want. So it's the first angle that you solve for, you find its supplement. So that's where we get that second set of answers from. Always that supplement. It's swinging that side over. So let's go ahead and do that calculation. So we're going to do our second set. So our set 2. We still have to start with finding that angle B. So we're going to find that calculation. Our new angle B, they'll use this little prime notation. It's 180 minus that angle B that we came up with originally. So the new angle B would be the supplement of that original. So the new angle B would be 180 minus the 61.4, so 118.6 degrees. So to find that first piece, it's pretty straightforward. It's just swinging that side the other direction to make that an obtuse triangle. All right, well then if angle B changes, guess what else has to change? Angle C and little c, right? Because if I made angle B bigger, that means C is going to get smaller. So we have to recalculate our new angle C. We're still going to be subtracting from 180, but we just have to subtract that new angle B. So we're going to subtract the 118.6 and still the 25. Your given information can't ever change. Angle A, side B, that's what they are. So we just have to recalculate the things that change. So our new angle C then would be 36.4 degrees. So it got smaller because angle B got bigger. Well, guess what? If side C gets, or angle C gets smaller, side C is going to get smaller as well. So we need to find our new angle C, or side C. So little c, or we'll call it C prime, just so we can differentiate from the original, is the sine of 36.4, our new angle C, as our side A, which was 26, is the sine of angle A, which is 25 degrees. So we do have to recalculate that new little c as well because it got shorter. So we cross multiply and divide. Our new angle C would be 26 times the sine of 36.4 degrees divided by the sine of 25. All right, so go ahead and calculate that. We'll get our new angle C. It will be shorter, so go ahead, pause, and type that in. And I'm coming up with about 36.5 feet. So our second set of answers come from the supplement of that first angle that we solve for, because again, we swing that side over and we can, instead of having an obtuse or an acute triangle, we have an obtuse, and that's what was happening in that first picture. So that's where that second set came from. All right, so let's recap. How did I know there were two solutions? Well, I knew there were two because it was a side-side angle. One angle was acute, side-side angle, and my side A, this A value, 26, was less than side B, but it was bigger than the height. That's the only situation that you'll ever get two triangles, because I can swing one way or the other. So again, thinking about that picture, either you can draw it going away from side A, or you can swing that side A back because it is longer than the height, and you can have this green triangle. And again, remember how to find this new angle B? It's always going to be the new angle B, the supplement of that first angle that you solve for, because this angle right here, since this would be isosceles, is going to be equal to the angle over there. This one on the other side will be its supplement. So that's where that second set is coming from. So that's the hardest one for people. It doesn't happen very often, but we need to be able to recognize it. All right, the rest of what we're going to talk about today is application and some area. So we want to talk about some different area things. We know how to find area when we talk about it in a regular situation. If I asked you to find the area, you would say 1/2 base times height usually, right? Area of a triangle. So I'm going to go ahead and draw a picture here. So we'll just have an ABC so we can have something to talk about. I'm going to go ahead and label this here. So if I gave you a triangle, normally I think what you'd be thinking is you would just do, to calculate the area, you would say 1/2 the base of this triangle times the height. Now the problem is, in a lot of triangles, we don't necessarily have the height, we don't want to have to calculate it each time, because usually what we know about triangles are either the angle measurements or the lengths of the sides, right? That's the pieces of information that we know. So is there a way that we can kind of replace that right away so we can have a formula that we don't have to calculate the height every single time that we do this? So let's see if we can make some conjectures here about how to do that. So we're going to derive this formula. So I want to see if we can figure out the height. So I'm going to have you look in this triangle right here. So say you know angle B, so we have that information, and say we have side C, we know that information, that's things that we would know about a triangle. Would we be able to solve for the height? So what side is the height in relationship to angle B? Well, the height is the opposite side, and then the C is the hypotenuse. So if you remember, this is how we calculated height before. We could do it for any of these. So the actual height in this triangle, we could set up by finding a just regular SOHCAHTOA ratio. Since this is a right triangle, it's exactly the same as what we were doing before to figure out our cases. So the sine of angle B would be equal to the height over C. And then to solve for the height, it would just be C times the sine of B. So it's really the same as what we were doing before. We just said B times the sine of A. You could do this from any vertex. So the labels don't really matter. We know that we can calculate that. So I know my height. So what if I, instead of call it height, what if I replace it with C times the sine of B? I can put that in to my formula for area of a triangle, so I don't have to calculate it each time. I just know what I'm going to use. And then the base of the triangle, well, what would be the base the way I have this written would be the A. That's what it's sitting on, right? The base is what the height is perpendicular to. So in this case, that would be the A. So I actually can put those both in, and I could say, hey, the area of this triangle is 1/2 times side A, and then let's plug in what we had for height, times side C, times the sine of angle B. Then everything's in terms of things that I would know about that triangle. I don't have to go through each time and figure out the height. Now let's take a look at what information you know about the triangle then in that situation. I'm going to use my highlighter here. So I know angle B, right? That's this. I know side A, which is that, and I know side C, which is that. So what I need to know is side, angle, side. Whenever I have that scenario, I'm going to be able to find my area really quickly. So I want to make sure that I have ways to be able to talk about that. So any area then, so any area of a triangle can be 1/2 the product of the lengths of the two sides times the sine of, we would call this the angle that is included in between. So the included angle. So it's a really easy way to remember. It's 1/2 side times the sine of that angle that's included. So we have lots of ways that we can write that. So the one we just did was 1/2 A times C times the sine of B. That's one version. That's using angle B. But couldn't I use angle C and the two sides? So I could do that one as well. So it could also be 1/2 A times B times the sine of C. But I could also do angle A, and what would be the two sides that includes that? Well, it would be the B and the C. So I can also do 1/2 B times C times the sine of angle A. Now, and remember, it doesn't even have to be ABC. You can have any labels that you want. So the idea is we just need side angle side. So that's kind of the big picture idea of this. If you know side angle side, you're going to be able to find area very quickly because I kind of figured out the height as part of that formula. So let's take a peek and see if we can try one. It says find the area of a triangle having two sides that are lengths 30 and 48 and an included angle of 40 degrees. Now notice there's no labels here at all, so I'm just going to make up a picture here. So I have a 30 and a 48, and the included angle is 40 degrees, and then I can just finish off my triangle. Notice there's no labels at all. This, in a real life situation, you don't walk around with things being labeled. So if I'm looking at this, I could put labels on it and use any of those formulas. Otherwise, just realize when you calculate area, I'm going to go ahead and write area, 1/2, you can think of it like this, side times the side times the sine of the included angle. So if you don't even want to put any sort of labels on these, you wouldn't have to. You could just say 1/2 30 times 48 times the sine of 40 degrees. And that would be my area. Notice I'm writing out the word area instead of saying A equals. Any idea why I don't want to just say A equals? Because A is often a label that I use to stand for a vertex, so sometimes I just actually write out area so people know what's happening. So this is a side angle side situation. If you think about what you're looking at there, I have a side length, so I have a side, and I have an angle measurement, and I have a side. So whatever labels you want to put on it, great. Otherwise, you can just do that calculation. So go ahead and multiply that out, see what you come up with. So our area of this triangle is about looks like 462.8. And what would the units be? These are in feet, right? So if it's an area and we're talking space inside, that is going to be in feet squared or square feet. So however you want to write that out. So just be careful. Our units do need to be adjusted accordingly. All right, let's take a look at some applications. All sorts of different things you can do with law of sines, tons and tons. This is kind of a cool one. Back in the 1850s, so think about how long ago with where technology was at then, surveyors used the law of sines to calculate the height of Mount Everest, and their calculation was within 30 feet of the currently accepted value. So with all the different technology we have today and satellites and being able to do all that imaging, they were able to, just with normal law of cosines, regular sighting equipment, we're able to do that. It's pretty cool. Take a moment and Google the height of Mount Everest if you don't know. There's been lots of movies and things about that, but it's kind of crazy to think people climb up there to the top of that. But pretty neat that you could use something like law of sines to do that calculation without having to actually climb up to the top to figure out the height of it to be able to do that. But Google it. It's kind of cool to take a look at that. We're going to take a look, though, at an example, a little bit easier one. And this is also can be something that's kind of interesting to figure out. Indirect measurement is some place, and I know we've talked about this with right triangles, is a place that we use calculations a lot. For example, if you take a look at this picture, say you wanted to take that tree down, you wanted to cut it down. It'd be super handy to know how tall it is before you drop it to make sure we don't land it on something. So you can do a quick calculation measuring how far you are away from the tree. You can measure your line of sight, so that angle of, remember what we call that, if we're going from the horizon opening up, what is that called? An angle of elevation, right? So angle of elevation is 23 degrees. We can measure that from the ground very safely. And we can also measure the angle that the tree makes with the ground, because we're on the ground. That's a very safe measurement. So these are things that would be easy for us to calculate without having to put our life in danger, but we can use what we know to help us solve. So here's what I'd like you to do. I want to see if you can figure out how to find the height of the tree using law of sines. See what you know about the triangle. What are you given? Think about both days, everything that we've talked about. See if you can come up with a strategy. Pause the video, give it a whirl. All right, so let's see what we know about the triangle. So we know two angles. So we have angle, side, angle is what we're given. So we have an angle and then a side and then an angle. Here's the cool thing about angle, side, angle. Can't you immediately find the third angle? And that's, I think, where we need to start, because the issue that we have is we do not know the angle currently that is across from the only side that we know. So if we're going to set up law of sines, we need to have that. So we need to find the third angle. So we're going to be subtracting from 180. So 180 minus those other two. So that's really the key beginning of this, is we have to realize that we need that other angle, which I believe is 61 degrees. So our third angle up here is 61 degrees. Now we know everything about the side and the angle across from it, so we can set up law of sines. So we have 30 meters is to the sine of 61 degrees as, okay, now which one do we want? Well, we want the height, and what's across from the height is that 23 degrees. So the height of the tree is to the sine of 23 degrees. So we can cross multiply and divide and solve. So let's go ahead and do that. So multiply across. So 30 times the sine of 23 degrees divided by the sine of 61. So cross multiply and divide. All right, so double check with what I came up with, like 13.4. Again, don't forget to finish off those parentheses. So 13.4 what? Well, these are in meters, right? So 13.4 meters would be the height of the tree. So you can make your projection like, okay, will I be able to cut that down right at the bottom? Am I going to take it down in parts? Definitely an important conversation to have before you start taking something like that out. So being able to express a non-right triangle situation and be able to solve is what law of sines is all about. So what it comes down to, unfortunately, is sometimes there's some ambiguity, right? So we'll go back and kind of, oopsies, talk through like what are the big pictures here. So angle, angle, side, angle, side, angle, really nice. We know one angle already, or two angles already. We can find the third. We can use law of sines. The side, side angle gets a little bit more complicated. That's where we have all of our cases that we need to keep straight. Always finding the height, comparing how does that side compare to the other side. Lots of thought that goes into that. And then we can find area too. So we can find area using our law of sines idea to help us solve a little bit more quickly when we don't have the height right away. So lots of things you can do with law of sines.